Hello, this is Mr. Gilmore with the 8.5, the Trigonometric Functions lesson. I'm about to introduce to you today three ratios that are going to change your life forever. Also, I'm going to introduce a really good friend of mine that's going to help you remember these ratios. Now, before we get into what is a trigonometric function, I do want to talk about a few of some of the variables that might pop up in today's lesson and future lessons. We're going to be talking a lot about angles in this latter half of our chapter 8. And because of that, we in mathematics typically use different variables to represent angle measures. And those variables represented are Greek alphabet letters. So I want to introduce to you three Greek alphabet letters that we will typically use to represent angle measures. We have alpha, beta, and theta. Okay, so these are the three symbols that are the, again, Greek letters, and we typically represent them with angle measures, and I want to make sure that you're not shocked when you see these. Like, what does this variable mean? Well, it just simply represents an angle. It's very much like we like to use x and y in the coordinate plane. We like to use these three typically when talking about angle measures. Now, also, before we get into our trigonometric functions, I want to talk to you about some perspective within our right triangle, all right? Because what we're going to be dealing with in our definitions of these trigonometric functions, that is what what adjective are we going to assign to the legs of the right triangle. Now, what I'm going to show you here are some adjectives we're going to apply to the right triangle based on the angle that we choose. So in the first part, we say, well, look at relative to angle A. Okay, so we have this angle A down here. So if we're standing right here in this corner where I'm going to put alpha, that's where we are. So from our perspective of angle A, I want to assign some adjectives to the two legs of our right triangle. Well, the first part is we have this adjective known as the adjacent leg, which is then the leg that is touching that angle. So the leg B is our adjacent leg to that angle. So I would apply the adjective to this side as the adjacent side, okay, or the adjacent leg. Okay, we still have our hypotenuse, right? That's still our hypotenuse. So that hasn't changed. But I am adding these adjectives to our legs now. So I have this adjacent leg to our angle. But then we also, from angle A, we have this side that is opposite of our angle A. It's as if I'm standing in a room and looking at the wall opposite of us. That wall, that leg, we call the opposite leg. And of course, that's all based on the perspective of where angle A is, right? Angle A is adjacent to side B or leg B, but it's opposite of the leg A. So what if our perspective changes? Okay, so now instead of standing at our angle A here, let's now move to our other acute angle here, angle B. So I'll just call that angle beta for right now. So now we're standing at the angle B's corner. How does our perspective change, and does it change our adjectives? It does, because this time the adjacent leg is not side B anymore. The adjacent leg is now side A, and the side opposite of our angle B or angle beta here, that is now our opposite side. And so notice that this is relative based on which angle we're standing in our acute, which of the two acute angles. Now the question does come up, will we ever stand in relative to angle C, the right angle? Not in Euclidean geometry. Outside of Euclidean geometry, when you move into some Algebra 2 and pre-calculus, they're going to tell you a story about the right angle. Our story begins with the acute angles. So merely just standing in our corners A and B and leaving angle C alone for right now. So our adjectives are going to be carried over into the next definition of our trigonometric functions. So keep this in mind that when you see these adjectives of adjacent and opposite, what we're really referring to is from the perspective of that angle in the given right triangle. So now let me introduce to you our three trigonometric ratios, these three functions that again will change your life forever: sine, cosine, and tangent. Now at the top you see in our title it looks like the word sin, cos, and tan. Those are simply just abbreviations for these three trigonometric functions. We have the sine function spelled S-I-N-E, the cosine function spelled C-O-S-I-N-E, and the tangent function, the T-A-N-G-E-N-T. And down below I have the definitions of these. Now the reason why I have them abbreviated in the title is you may have seen these on your calculator before. You may have come across these words on your calculator going, what are these things? Well, these things represent a function that apply to right triangles. So let's define what are these functions. What do these functions do for us in a right triangle? Well, first, before we dive into the definition, up above, let's let angle alpha be the measure of an acute angle of a right triangle. So pick any right triangle, make any right triangle, and let's pick the acute angle to be alpha. Then we're going to put this in terms of alpha in our definition, okay? So for our first definition, the sine of alpha. The sine of alpha is abbreviated sine alpha. So we see it looks like the word sin alpha, okay? Sine alpha is the ratio. That's a key word, okay? These are trigonometric ratios, trigonometric functions. Is a ratio of the opposite leg to the hypotenuse. So what we're doing with this function is we're actually creating ratios of our sides in a right triangle. And you'll see that the other two functions, are cosine and tangent, do the exact same thing. They make other ratios inside of our triangle. Let's take a look at our cosine of alpha. So second definition. The cosine of alpha, again abbreviated cos alpha or cosine alpha, is the ratio of the adjacent leg to the hypotenuse. So remember, this is all based on the perspective of our angle alpha. So now we have a different ratio, adjacent leg ratio to the hypotenuse. And then we have our tangent function. The tangent of alpha, abbreviated as tan alpha, is the ratio of the opposite leg to the adjacent leg. So what we're doing with these three functions are forming ratios of the sides. And what actually happens is because of these relationships of these ratios, there's some magic numbers that appear. We'll talk about these numbers here in a little bit. But let's first talk about, well, what do we do with these, or how do I remember these definitions? Let me introduce you to a good friend of mine known as Sohcahtoa. So go ahead and say to yourself, Sohcahtoa. It's actually kind of fun to say, Sohcahtoa. This is essentially an abbreviation, or kind of like, not necessarily a mnemonic phrase, but an abbreviation to help you remember these three ratios, these three definitions of sine, cosine, tangent. Each one of the three parts in the word Sohcahtoa represent one of the three definitions. Let's start with the first part, so. Okay, if you look at our first ratio of our definition of sine, this is what unfolds from the definition. It says that the sine of alpha is equal to the ratio of the opposite leg over the hypotenuse. Now what we do, and you see that I've bolded this, we steal the first letter out of each word, S-O-H, and we make the word so. So when we say so, as part of Sohcahtoa, what we're really doing is trying to remember, well, what's that ratio? Oh, that's right. So means sine of alpha is equal to opposite over hypotenuse, right? So sine is opposite over hypotenuse. For the middle part, ka, that moves into our definition of cosine. We have cosine of alpha, by definition, is the ratio of the adjacent leg over the hypotenuse. Again, steal the first three letters, C-A and H. Put them together, we get ka. And ka then helps us remember what the definition of cosine is. Oh yeah, cosine is adjacent over hypotenuse. And then our last part, toa. Toa is then our definition for tangent, right? Tangent, by definition, is tangent of alpha, is the opposite leg over the adjacent leg. Steal the first letters of the words, and we have toa, T-O-A. And that helps us to remember the definition of the tangent function. So we put them all together, and we have our very new best friend, Sohcahtoa. And you will find, even us experienced math teachers, we will still use Sohcahtoa to help us remember these ratios. In fact, if you when you move on to Algebra 2 and to pre-calculus, you'll be seeing that Sohcahtoa is, again, going to be one of your good friends that you're going to want to hold on to and remember, to help you remember your three relationships of sine, cosine, and tangent. So let's actually bring these ratios to life. So I've got an example here of this triangle that's just been generically labeled. We have our three sides, A, B, and C. Right, A and B are the legs of the right triangle, C is the hypotenuse. And I have our two acute angles labeled. Now remember, these functions work with acute angles. And we'll talk about what a function is here in a little bit, about the input and output and things like that. So the triangle in our diagram, we have alpha and beta as our acute angles, and we're gonna find then the sine of each of those angles. So we find the sine, cosine, and tangent of angle alpha, and then repeat that sine, cosine, and tangent for angle beta. So let's start with angle alpha. So we're starting here in this corner. Well, the very first thing you remember with any angle that you choose, any acute angle, is you have to remember perspective. The leg that it's adjacent to, right, we then name the adjacent leg. That's the one that's touching our angle. The leg that's opposite of our angle, we call the opposite. So with this, from our perspective of angle alpha, we now know which is our opposite leg, which is our adjacent leg. C will always remain the hypotenuse regardless. It always stays the hypotenuse, okay? So now let's do the sine of alpha. Well, sine, think about what Sohcahtoa says. Sine is the opposite over the hypotenuse. So I'm looking at the opposite leg, which is my side B, over my hypotenuse, which is side C. And there we have it. That's our sine of alpha. Sine of alpha is B over C. What's the cosine of alpha? Okay, well, cosine is then adjacent over hypotenuse. So the adjacent leg is A, and the hypotenuse is again C. There's our ratio of cosine of alpha. Cosine of alpha is equal to A over C, the ratio of those two sides. Now, tangent is TOA, the opposite leg over the adjacent leg. So my opposite leg is B, my adjacent leg is A, again from the perspective of alpha. So my ratio is B over A. Now let's change perspective to move into our second acute angle, angle beta. Now our perspective changes. The two sides switch their adjectives. Side B now becomes the adjacent side. That's the one that's touching our angle B. And then the leg opposite of our angle beta is our opposite side here. Now we go back to Sohcahtoa and we rinse and repeat. What's the sine of angle beta? Well, so is opposite over hypotenuse. So what's opposite this time? A is the opposite side. Hypotenuse doesn't change, it's still C. Now K is our cosine of beta. We're going to go the adjacent leg over the hypotenuse. That's side B over C. And then the tangent of angle beta, that's the opposite leg over the adjacent leg. So we do that one again, and we have A over B, right? The opposite leg over the adjacent leg. And you're going to notice some pattern with these relationships of sine of alpha, cosine of alpha, and then if you notice, there's patterns between the sine of beta and the other acute angle. And you're going to investigate some of these patterns on the worksheet. Now let's actually apply some numbers. Okay, let's put some numbers on our triangle, make it a little bit easier to find. Say, okay, let's find the sine of angle A, sine of angle B, and we're going to find all these trig ratios with cosine and tangent of each of the two acute angles A and B. But in our triangle now, we've got some numbers. Still, our best friend is going to be Sohcahtoa. Okay, following the relationship of our three definitions. So sine of angle A, so that means I'm standing in this corner right here, so I'm using angle A now for my perspective. So that means my opposite side, I'm just going to label as O from now on, is 15, and then my adjacent side is side 8, which is my adjacent side. And again, my hypotenuse doesn't change, that is still 17. So now let's do so. Sine is the opposite over the hypotenuse. So sine of angle A is the opposite over the hypotenuse. So we get a ratio of 15 to 17. There we have it. There's our answer for sine. Let's move to cosine of angle A. So cosine is the adjacent side over the hypotenuse. So use K this time. So adjacent is 8, hypotenuse is 17. And then tangent is my opposite over adjacent. That's TOA. So opposite over adjacent, that's 15 over 8. And there we have it, my three ratios for the sine, cosine, tangent of angle A. Now let's change perspective and move to angle B this time. So my opposite side now is 8, and my adjacent side now is 15. So sine of angle B, opposite over hypotenuse, so that would be then 8/17 this time. Cosine of angle B is adjacent hypotenuse, right, K, so that would be 15 over 17 this time. And then tangent of angle B is then the opposite over the adjacent, that's TOA, and my opposite is 8, and my adjacent is 15. So there we have it. I filled in all my trig ratios of angles A and B respectively from their perspective of our three sine, cosine, and tangent functions. Now, is this going to be the same for all? Meaning, if I'm given an acute angle alpha, let's say the measure alpha, is the sine of alpha, or I should say the cosine or tangent of alpha, always going to be the same ratio in any right triangle? Well, the simple answer is yes. If I took the sine of an alpha for one right triangle and the sine of alpha for a second right triangle, they would be the same number. They'd have actually the same ratio. But why is that? Well, it's because of similarity, right? If I have alpha as an acute angle in one triangle and alpha as acute angle in the other, if they're both right triangles, that means by angle-angle similarity, I automatically know the two triangles are similar. Let's take a look at a picture of these two guys. So here are two triangles, each with the sides labeled in one A, B, and C, and then the other RST. And you'll also notice that each triangle also has the measure of alpha in it, which means those angles are equal. And since they also have the right angle in it, that means we do have two angles of one triangle equal to two angles of another. So then by angle-angle similarity, we can call these two triangles similar. Well, what we're going to do is show that the sine of the first triangle sine of alpha of the first triangle is equal to the sine of alpha of the second triangle. So where we begin is, let's actually begin with the proportional sides. Since these two triangles are proportional, that means, or so similar, that means their sides are proportional. Now, in particular, the portion I'm looking for is I'm going to go the opposite over adjacent because I am working with sine. So think about so says opposite over adjacent, or sorry, opposite over hypotenuse. So I'm going to use my opposite and my hypotenuse sides from angle alpha. So the opposite and the hypotenuse in this case for my first triangle would be B over C. And I know that to be the same ratio, since these triangles are proportional, that means the sides are proportional, it's going to be the same ratio in our second triangle as its opposite side over hypotenuse. So B over C is equal to S over T. Okay, so we know that that is a true proportion, right? That's a true proportion based on our similarity. But what do we know about these two ratios? Well, the sine of alpha, okay, of our first triangle, I'll say sine 1, this is our triangle 1 of alpha. So sine 1 of our alpha is the opposite over hypotenuse, which means it's equal to that ratio, B over C. And our second triangle has a same alpha, right? So it's sine, I'll call this sine 2 of alpha, same alpha. It's also opposite over hypotenuse, which is S over T. So notice that then, because these have these proportions, this proportion was true by similarity, and these definitions here are true by the definition of sine, that means these two things must be equal to each other. So the sine of our first triangle of alpha is in fact equal to the sine of alpha of our second triangle. So yes, okay, if I take the sine of any angle for no matter which size right triangle it is, it'll always come out to be the same number. It'll always come out to be the same value. So sine of any angle, sine of alpha, equals the sine of alpha of any other second right triangle. Now we call these three ratios functions. Okay, so we call the sine a function, the cosine a function, the tangent a function. What do I mean by function? That means there's a rule. This rule takes in an input, and for that given input, it does something to it. It's like a machinery. It does something to that input, and then it delivers a unique output. So there's an input, some sort of process, and then an output. That's what a function is. So for our sine, cosine, and tangent, what are their inputs? They take in acute angles. That's what an input is. So I put in an acute angle measure into the sine, into the cosine, or into tangent. And then for each of those acute angle inputs that I put in, it gives me a unique output. So what is then that output that it gives? It gives me the same ratio. Okay, so it's going to give me a number back, and that number that gives me back is a ratio, and that ratio is respective to those three functions. It's either going to be the ratio of the opposite of the hypotenuse, the adjacent over the hypotenuse, or the opposite over adjacent, because those are my three functions, sine, cosine, and tangent. So thus, these are considered functions. These trigonometric ratios are really functions. I give them an input, and they give me an output. So let me really break down what to think about when you see a function written out, such as the sine of 36 degrees. So here's our expression. And the way we read that, I read that as sine of 36 degrees. So what does this sine part represent? The sine part represents our function. That's the rule. That's what it's going to do. It's the process at hand. It's very much like when you do a square root. That's the rule. That's the function. It's going to take the square root of then a number. So the sine is going to then process the input. Well, then, so the sine part is the function. What about the 36 degrees part? That part is the input. Remember, that's the acute angle measure. So we're putting 36 degrees into the function of sine. And again, that's why we read that as the sine of 36 degrees. So then the whole thing, what is the whole thing? The whole thing then represents the value, which is that unique output. The whole thing represents the value of the sine function for the input of 36 degrees, which of course is going to spit out a number. That number is going to be the ratio of the respective sides. In this case with sine, it's going to be the ratio of the opposite of the hypotenuse. So then, the sine of 36 degrees is going to be the same as sine of 36 degrees, which is going to be the same as sine of 36 degrees, which means no matter which right triangle, it's the same for all triangles. It's going to output some unique value, give us some unique output of a ratio. But the real question is, how do we get that number? Where does that unique number come from? What do we do to understand if I plug 36 degrees in? Like, I know how to take the square root of 4, it gives me 2, but I don't know what it means to take the sine of 36 degrees. So where do we find that number? Where's that number come from? Well, let me put an emphasis on that. We don't find those numbers. Those numbers have already been found for us, which means there is going to be a table of values that already been generated for us, and I'm going to give you that table of values. So in person, in class, I'm going to provide this table of values for you. It's a paper copy, and also you're going to find this as a digital copy linked on Canvas. And this table of values has been discovered for us. The mathematicians before us have come together and figured out ways to find what are the values of a sine of 36-degree angle, right? If I plug sine of 36 degrees into my calculator, it spits out a number. Well, where'd that number come from? It's because it's already been discovered on how to discover it. And the reason why we're not going to figure out these numbers is because it does involve some level of calculus and some understanding there, which means we're going to avoid that and just say, hey, thanks for these numbers. We're going to take them as they are, and then we will use those table of values as we move forward in our examples. So again, we have two resources. We have the table that I'm going to provide for you of knowing what the sine of 36 degrees is or any other acute angle measure, and also we will be allowed to use our calculator. So just for practice, let's do a little table or calculator work. And what I mean by evaluate is, remember, these are functions. For number one here, it's going to, sine is our function. It's going to take the input of 49 degrees. So the whole thing, sine of 49 degrees, is going to give us a number. That number is a ratio. So what I'm going to do is plug this into my calculator, and I'm going to write down what number it spits out. Or I'm going to take a look at my table. Now, our table is rounded to the nearest 4 decimal places. I'm going to do the same thing on my calculator, just round to the nearest 4 decimal places. So on my calculator, I type in sine of 49 degrees, and what it outputs, again, this is a unique number, 0.7547. There are more decimal points that follow, but I'm just going to stop there. Okay, so that is, again, we don't find that number. That number has already been found for us. We're going to let the calculator do the work, and we're going to do the table do a work with us. But this is how we find those numbers. We can actually find them from our table, and we can find them using our calculator. So now I'm going to plug in the cosine of 36 degrees. So cosine is our function. I'm going to plug 36 degrees into the cosine function, and you'll find these on your calculator, or just follow the table, find the 36-degree value, and then find what the cosine of that 36-degree value is. And it puts out a number, a unique value of 0.8090. Now, of course, I don't really need that last zero on there, but if I'm going to stop at 4 decimal places, I'm going to stop there. So 0.8090 is what the cosine of 36 degrees is. Now, to finish it off, I'm going to use my tangent function, and I'm going to input the number of 24 degrees into it. So the tangent of 24 degrees is going to output a number I can use at my table or on my calculator. And again, I'm going to stop at 4 decimal places, 0.4452. Okay. So each of these is going to give me a number, right? And of course, I can plug in really any acute angle measure. I can do cosine of 29 degrees, sine of 84 degrees. As I move up and down my table, you'll find those values of any acute angle measure that we plug in. Okay. Of course, the table is going to come in handy, but really the calculator, now that we're at a time where we have this ability to calculate these values very quickly, the calculator is going to become one of the better tools in this case to evaluate what these function ratios will be. Now, what is it good for? Why are we studying what the sine of this angle is, or the cosine of that angle is? Why are we studying these acute angle measures? Well, think back over the previous lessons we had in this chapter. Really what we've been able to discover is the relationship between our side measures and angle measures within a right triangle. So for example, we found the Pythagorean theorem. And the Pythagorean theorem said, hey, if you've got two sides of a right triangle, we know the relationship of all three sides, a squared plus b squared equals c squared, which means you can find the missing third side if I give you any two sides of a right triangle. And then there was the special right triangles. And special right triangles said, hey, with these special angle measures, you can find any side measure by knowing only one of the side measures. But now we're at a point where we want to broaden this and say, well, what if I know a side measure and an angle measure of my triangle? Can I still find any of the missing side measures? And we can with our new trig ratios, our trig functions of sine, cosine, and tangent. Let me walk you through this example and show you why these are good. So in my diagram below, I have this right triangle here with the two legs missing, x and y. I have an angle of 72 degrees given to me as my acute angle, and I'm given the hypotenuse. With just this information here, I can actually use this to find our missing side measures, x and y. So I'm going to use this trig to figure out our missing side measures. I'm going to start by finding the missing value of x. Now, before then I dive into, well, what equation am I going to create? I'm going to then label my sides so I know what my adjectives are. So the adjacent side of 72 is x. The opposite side of 72 is my side y. That's my opposite side. And then I still have my hypotenuse here is my 32. So now that I have my three sides labeled with my adjectives and my hypotenuse, I can then dive into, well, what function am I going to use to find this missing side of x? Well, x is the adjacent side, okay? So I need to know I'm working with a ratio that involves the word adjacent, all right? So my Sohcahtoa, take a look at this guy. Sohcahtoa, I see that adjacent is used twice. It's either, I will either use cosine or tangent. I see the a value there, or a adjacent adjective there. It's not in sine, so no, I'm not going to use that one just yet. But what other side am I given in my triangle? I'm given my hypotenuse. So I'm narrowing down which function to use. I want to find the adjacent side, and I have the hypotenuse. Which function uses both of those sides, adjacent and hypotenuse? That's right, it's the cosine. So my cosine says this: cosine of my angle alpha is equal to the adjacent side, adjacent leg, over my hypotenuse. Well, what that means is I have two of those three variables. I have the angle, I have the hypotenuse. I can figure out what my adjacent side is, which is my side x. So let's fill this in. I have the cosine of 72 degrees is equal to my adjacent side, which is x, over my hypotenuse, which is 32. That is one equation, one variable. I can isolate x to get it by itself and solve for what this is. Now remember, cosine of 72 is just a number. Let's figure out what that number is first. So I'm going to put that on my calculator or look at my table. When I do the cosine of 72, it gives me this, 0.3090. Okay, so I just replace that. Then I have this x over 32. I want to get that 32 by, or the x by itself. So what I can do is, since it's being divided by 32, I simply just multiply both sides by 32. That cancels out there. I'm going to flip my equation around to bring x to one side. Then I do 32 times that, what really was cosine of 72, which is now that decimal by ratio value, 32 times 0.3090, and it gives me this number, 9.888. I'm probably just going to round that to the nearest tenth and just say 9.9. So there we have it. We just found our missing value of a side using a trig function. Let's solve for y now. Let's figure out what y is. In this second case, trying to figure out the second variable here, y, I have to use now the opposite side, right? It's the angle, the side opposite of my angle. So I know I'm going to use the letter O. That narrows it down to either my tangent or my sine. So it's one of these two now. But again, I'm given my hypotenuse. So if I want the opposite and I have the hypotenuse, which trig ratio relates to both of those? O and H, that's my sine. So, which means I'm going to use the sine function this time. Sine of alpha is equal to my opposite over my hypotenuse. Plug in the numbers we know. Well, it's the sine of my alpha, which is 72 degrees, is equal to the opposite side, that's my y value, over my hypotenuse, which is 32. Now, sine of 72, remember, is a number that says, well, the sine of 72 is going to give me the output, the ratio. Well, if I put that in my calculator or look at my table, sine of 72 is 0.9511. And I can solve for my y value now by isolating the variable. I'm going to multiply both sides by 32. That cancels out, so I get y is equal to 32 times 0.9511. That spits out 30.4352. Again, I'm just going to round that roughly to 30.4. So there we have it. We found both of our missing sides of our right triangle only using an angle and a side measure given to us. And that's the power of trigonometry. What we can do is what we call solving triangles, meaning we're finding all the missing measures. We can find all the missing angles and all the missing side measures using we're using the power of trigonometry. Now, before we move into one more example, I do want to introduce a new convention to you. And this convention is in particular to naming a triangle. When you draw out a right triangle, or really any given triangle, what we do is we let the capital letters represent the angles, and we let the lowercase letters represent the sides. However, in our diagram below, notice that there's a little bit of a strategic labeling with our sides and our angles. So if I label my three angles A, B, and C, I'm not just going to be all willy-nilly with my my lowercase letters A, B, and C. What I'm going to do is I'm going to make sure that the lowercase letter that's respective to its uppercase letter is the opposite side of that angle. So notice that angle A, the opposite side of angle A is lowercase a. Angle B, the opposite side, is lowercase b, and angle C, the opposite side, is lowercase c. That's our typical naming convention when we dive into triangles. So if I were to draw just any random triangle, and let's say I call this RST, then the way I would label it is the side opposite R, I would call that lowercase r. The side opposite S, I would call that lowercase s, and the side opposite T, I would call that lowercase t. And that's the naming convention we are going to use from now on when we dive into right triangles, or really any triangle that we draw. We're going to use this proper naming convention. So now here's another example of finding some missing side lengths of a right triangle, but notice I didn't give you a diagram. What we're going to do is generate our diagram based on that naming convention. So the given says in our triangle ABC with right angle C, B is equal to 12, angle A is equal to 42 degrees, and we're going to find the missing sides of A and C. So what I'm going to do first is draw out our given, a right triangle, such that our right angle is C, so it doesn't matter where I put A and B. I'll put A down here and B up here. It doesn't really matter where I put them, as long as angle C is the right angle. And now follow our naming convention. So the side opposite of our capital A is going to be lowercase a. The side opposite of our capital B is going to be lowercase b. And a side opposite of angle C is going to be our lowercase c. But what I can do is go back through and fill in what I know. I know the side B, which means I know this side is going to be 12. And I know what the angle measure of angle A is. That's 42 degrees. Well, we have an angle and we have a side, which means we can use trigonometry, our sine, cosine, and tangent functions, to find our missing measures. Let's start with finding missing value of A, okay? So from the perspective of my angle, this side A would be my opposite side, and then the side 12 would be my adjacent side, and again, side C is always the hypotenuse, okay? That's always the hypotenuse. That doesn't change. All right, so I'm going to try to find the opposite side, and I'm given the adjacent side. So go back to Sohcahtoa. Which trig function is going to use the opposite and the adjacent side? That's our tangent function. So its tangent of alpha is equal to the opposite over the adjacent. Let's plug in what we know. We know that our tangent of alpha, so it's tangent of 42 degrees, is equal to our opposite, which is side A, over our adjacent side, which is side 12. Well, tangent of 42 degrees, remember, is just a number. So that number comes out to be 0.9004. I got that from my table. And I am going to simply then solve for A by multiplying both sides by 12. Those cancel out. And then I'm doing, so A is then equal to 12 times this 0.9004. That spits out 10.8048. I'm going to, again, round that to the nearest tenth and just do 10.8. So there's my missing side for value of A. Now I want to find my missing value of C, okay, my hypotenuse. Now again, I'm given my adjacent side, and I want to find the hypotenuse. Which trig ratio uses A and H? That would be cosine, the right, A and H. So the cosine of my alpha is equal to the adjacent over my hypotenuse. Plug in what we know. My cosine of my angle, 42 degrees, is equal to my adjacent side, which is 12, over the hypotenuse, which is C. Now notice something's a little bit different with this ratio. My C value is in the denominator. And I'm going to show you a little quick algebraic trick here in just a second. So the cosine of 42 degrees, go back to that. That is just a number. It's a ratio. I get that ratio from my table or my calculator. I get 0.7431 as I plug that in my calculator, or just take a look at my table. And I'm going to now solve for my C value. Now, here's the problem. A lot of students make this mistake. They think, I'll just multiply both sides by 12 and it cancels out like we did on the others, like we did with our tangent. It doesn't work the same way, okay? I can't just multiply both sides by 12 because the 12 is not in the denominator. My 12 is in the numerator. But there's this really neat algebraic trick that I'm going to show you here, that if you have a situation like this where the variable's in the denominator, what you can do is actually take these two numbers and just switch them, okay? It's because what we're really doing is those are the extremes of a proportion. You may actually move the extremes around. So just flip the location of the extremes around, move C to where the 0.7431 is, and move that 0.734 to where C is. And what we'll do is then isolate our variable. So we get a C is equal to 12 divided by this 0.7431. And we pop that into our calculator and solve. We get C is 16.1486. And again, I'm going to round that to roughly 16.1. So there we have it, finding our missing side measures using trigonometry. Now, I know that's a lot to absorb in this lesson. Sine, cosine, and tangent, again, are going to change your life for the better. They allow us to solve right triangles with having angle measures and a side measure. Please be sure to hop over to the 8.5 worksheet and be working on that worksheet with using sine, cosine, tangent, our new trig ratios. If you have any questions on that assignment, please don't hesitate to email me. With that, be good and do good.